In lecture 8 of Symmetries, Particles and Fields, we will examine the SO3 tensors in more generality, indicate how you can generalize to SON, and then we'll talk about what happens when we discuss tensors of SUN. And for the latter half of the lecture, we'll move to a new chapter, which is on SO3 and SU2, and in particular, we'll build up the representation space of SU2. So from the discussion last lecture, we see that it's the indices that play a crucial role. And this is true for general groups. And a general number of indices. In particular, if we sum over all indices or pairs of indices, then the result is invariant. Under the action of the group. The invariant tensors help us build up invariant subspaces. And if we took an SON theory instead of SO3, we have invariant tensors to be the Kronecker delta of alpha beta, where alpha and beta, etc. are alpha and beta are in 1, 2, up to n. And we have an n-dimensional, totally anti-symmetric symbol with n indices. So for general G, for general groups, one can build up these tensor representation spaces to arbitrarily many indices. Last time we saw examples with 0, 1, and 2 indices. So in that case, we started with the lowest rank tensors and built up, making sure that we subtracted any lower rank tensors that were hidden in the ones that we were considering. And that's the way to do it algorithmically. You start off with the lowest rank ones, you build up, subtracting any lower rank ones that are hidden in what you've got, to build them all up. So we use the invariant tensors to do that. Build up the lowest dimensional, irreducible reps. And then we start increasing the rank and removing any lower dimensional subspaces, which are invariant, any lower dimensional invariant subspaces. So if we go back to SO3, and we want to consider a general n-index tensor, we impose that the trace over any two indices. So let's take some n-index tensor, Si1 to In. And so the trace over any two indices has to be 0. And the anti-symmetrization over any two also has to be 0. So this is where R would not be S. So if we impose those two conditions, then we guarantee that the lower dimensional subspaces, invariant subspaces, have been removed. So if we can solve these two conditions, then we can write down our invariant, our irreducible representations. So in fact, they're easy to solve. So firstly, we must have that the tensor that we're considering is symmetric in all of its indices. That will guarantee that it's not anti-symmetric in the switching of any. So when we have n indices, we have an implicit 1 over n factorial, and then we symmetrize over all indices. And secondly, oh, sorry, I should say, this condition implies that the representation space is in the symmetric part of the tensor product of 3 to the n. And B, our second condition, we have that Sin I1 to In minus 2, and then the trace on the last pair is equal to 0. Since it's symmetric, it doesn't matter which pair we pick. So it's sufficient to require that it's just traceless on the last pair. So if we count the number, we can count the number of degrees of freedom in our tensor now that satisfies these conditions, and then we can count the number of degrees of freedom in our irrep. So any tensor with R indices equal to 1, S indices equal to 2, and T indices equal to 3 is identified with the other tensors with that number. So what we're going to do, this is looking at the condition A. Because we've symmetrized over all indices, it doesn't matter the position of those indices. And so all of these tensors are equal to S where we put all the ones first, so we have R of those, and we put the 2 second, we have S of those, and we put the 3s third, and we have T of those. And because there are n indices in total, so R, S, and T are in the natural numbers, including 0, and R plus S plus T is equal to n. So if we count all different possibilities for R, S, and T, we can count the dimensionality of this rep space in this symmetrized vector space. So counting all R, S, and T satisfying this, then the dimension of this symmetric space is, well, R can vary from, you can have 0 ones or you can have up to n. So R goes from 0 to n, and then S, we can have 0 number of 2s, or it can go up to n minus R. And then we use this equation above to find out what T is. So those are your different dimensionalities, and each one comes with one different option. And so all we have to do is sum this up, and we get half n plus 1 times n plus 2. So we haven't applied the traceless condition yet, but at least this first condition gives us this number of dimensions. And for the second condition, it's sufficient to subtract the rank of dimension n minus 2 symmetric tensors. So there are the same number of conditions as the rank n minus 2 tensors in this one here. Since the trace removes 2 indices. So in other words, the dimensionality of our representation space is a half n plus 1, n plus 2, minus the number of conditions, which is, well, it's the same formula, but with n minus 2 inputted for instead of n. And this gives us 2n plus 1 as the dimensionality of the rep. This is equation 3.2. Okay, good. So there is an exercise in the book, which is a little more tricky, where you do this for you do the same exercise as we did for 2 indices for a 3-index tensor. And again, you need to define, scalars, and then build up and subtract out the lower dimensional representations by using invariant tensors. And you have to make sure that all of the tensors at a certain rank that you're introducing, you want the linearly independent combinations. And we didn't see any problem for 2-index tensors, but for 3-index tensors, for some of them, they're not always absolutely independent. So that's worth trying. Although because it's a bit tricky, it is an optional exercise. For SUN, now, the difference with SUN is that we have a complex representation space. So we need to discriminate between fundamental indices and conjugate indices. So we must discriminate between the fundamental rep and its conjugate. So we do this by upstairs and downstairs indices. So let's take an n-dimensional complex field phi. Okay, so it's going to be a function of x mu in the fundamental rep of SUN. So and phi will have I as the SUN index. So this transforms like an n-dimensional rep. So under SUN, this goes to U, I, J, phi j. So we have the fundamental representation indices downstairs. So U here is a member of SUN. Under SUN, on the other hand, the phi dagger has an index upstairs. This transforms as the conjugate rep, which we denote with a bar on the top. And this goes to phi dagger j, U dagger I, j. Sorry, I guess I should write it in that order. So the conjugate indices go upstairs. And that's all it means. The index either transforms with a U dagger or a U, and that's determined by whether it's up or downstairs. So here, I and j are in 1 to n. So what are the basic invariant tensors now? As well as a scalar. So in SUN, they become delta ij, which is Kronecker delta, and two totally antisymmetric tensors. Epsilon I1 to IN with the indices upstairs, and epsilon I1 to IN with the indices downstairs. So because we're in SUN, if we have U dagger, then that just gives us the identity. So what that means is that phi dagger I, phi I is UN invariant. So immediately we can see how to write down our four-dimensional renormalizable Lagrangian in terms of this complex field. We write the kinetic terms like this. We have the mass term, and we always have this combination where we've summed over this index, effectively using the Kronecker delta. And that would be our SUN invariant Lagrangian. So what about tensors with more indices than one? Well, general SUN tensor has some upstairs indices and some downstairs ones. And of course, under SUN, for all of the downstairs ones, we get, 1 second. Yeah. We get a factor of u. And for all the upstairs ones, we get a factor of u dagger. And the number of indices on the upstairs and downstairs can be different. And so we have T. Okay. That's how our general SUN tensor transforms. For the conjugate for its conjugate representation, then what we know is that the upstairs and the downstairs indices should swap. And so that's what happens when we take the complex conjugate. So upstairs and downstairs switch. The number of upstairs indices switches with the number of downstairs indices. Now, SUN, in fact, in particular, SU2 and SU3 find a lot of applications in particle physics, and we'll return to those later. Okay, so now we start a new chapter, and that's on SO3 and SU2. These are important because in some sense they're the simplest non-trivial Lie groups. And in fact, we're going to start off with the representation theory of the Lie algebra of SU2. And this is going to help us, it turns out, but by analyzing this and working out its properties, this will help us analyze the representation spaces of general groups later on in the course. So this is chapter 4, and it's representation theory of the Lie algebra of SU2. So so this is, remember, we saw that this, where sigma A of the Pauli matrices is a basis of the Lie algebra of SU2. And you know, that's a perfectly good basis, but it's going to be convenient for us to define a different basis. This is called the Carton Vial basis. It's neither Hermitian nor anti-Hermitian. This Carton Vial basis is the one that we'll use to generalize to different groups and different Lie algebras. The Carton Vial basis of the Lie algebra of SU2 is the following. So actually, we have this element H, which is just the third Pauli matrix. But then we define something called E plus, which is a half sigma 1 plus I sigma 2. So if you actually do that matrix summation, you'll find that this is 0, 1, 0, 0, and E minus, which is a half sigma 1 minus I sigma 2, and this just has a 1, oops, in the lower left-hand corner. So we need to work out our Lie brackets of these different elements, basis elements, and you can do that with just matrix commutation. So if you check it, you should check these, that H commuted with the matrices that represent E plus and E minus give us plus or minus twice times E plus or minus. And the commutator of E plus with E minus gives us H. Right, so what this top equation means is that with E plus or minus, we can change the eigenvalue with respect to H by 2 units. So we call E plus or minus ladder operators. Okay, so in this basis, we can work out what the adjoint rep with respect to H is of H, for instance. So this is the commutator of H with itself, but it's a diagonal matrix. So its commutator is 0. And the adjoint rep with respect to H of E plus or minus from the commutation relations is plus or minus 2 E plus or minus. So what we see is that the Carton Vial basis elements, we can call these generators. These are eigenvectors of ad H. H, E plus and E minus have eigenvalues of 0, 2, and minus 2, respectively. So these eigenvalues are known as the roots of the Lie algebra. So actually, this mirrors the way that we're going to analyze general groups Lie algebras later. Okay, so what I want to do now is consider a finite dimensional representation of the Lie algebra of SU2. With the representation space V, and assume that representation of H is diagonalizable. Then V is spanned by the eigenvectors of D of H. In other words, these eigenvectors are going to be V suffix lambda, and the eigenvalue is lambda. These are the eigenvectors. So lambda in general are complex numbers, are eigenvalues. And they're known in this context as the roots of D of H. Sorry, the weights. Okay, so let's consider what D of H does when it acts on one of these eigenvectors. Which has itself been acted on by DE plus or minus. Well, I can just use the commutator. So I can add on and subtract. I can subtract from this E plus or minus, D of E plus or minus times DH, and then add it on again. And remember that for representations of Lie algebras, this is going to be the representation of the Lie bracket of H plus and E plus or minus. What's this Lie bracket? Well, we go back up and we find the Lie bracket here. So this is plus or minus 2 E plus or minus. Okay, so this whole left-hand side is equal to lambda plus or minus 2 d e plus or minus v lambda. So what this means is that when we act with these ladder operators on our representation space, we get another eigenvector of the representation of H, or it's equal to 0. Okay, so we've chosen finite dimensional representations. And what we've seen here is that we can change the eigenvector by 2 units. And so there must be a highest weight if this is a finite dimensional representation. Otherwise, we'd be able to have infinitely many independent vectors in our representation space. So since D is finite dimensional, it must have a highest weight. So we'll call that big lambda, complex number in general. And that's defined by D of E plus V lambda gets annihilated. Otherwise, we'd obtain infinitely many independent vectors in V, and it would be infinite dimensional. So if D is an irrep, we expect to find all remaining basis vectors of V by acting on V, this highest weight state, with lowering operators, with E minus. So we define some vector lambda minus 2L, which is defined to be d e minus to the nth power acting on v of lambda, where here L is a natural number. Okay, so what this implies is if we act on this v of lambda minus 2L, what we're going to find is that our eigenvalue is lambda minus 2L. And we define, well, we also have that d of e minus just lowers the eigenvalue by 2 units. Oops. And we also have, well, we're going to make a definition now that if we raise this act up with a raising operator on this vector, this eigenvector, we're going to define that to be some constant RL, which is complex, times the vector with 2 added to its eigenvalue for some RL is complex. So that's really a definition of RL. Now we can find what this constant is. We can find a recurrence relation so d of e plus acting on v of lambda minus 2L is equal to d of e plus d of e minus acting on v lambda minus 2L plus 2. That's just because this combination is equal to this vector. So again, we can use the commutator between these two things. So this is okay, and you just substitute in for what this commutator is, and we'll get lambda minus 2L plus 2 plus d e minus d e plus it's going to be lambda minus 2L plus 2. Okay, there's a couple of lines just to show that this implies that because on the left-hand side, we have something proportional to, well, what we've got is RL times V lambda minus 2L plus 2. So this implies that RL is equal to RL minus 1. Because on both the sides, we have this, we're going to have this vector now, RL minus 1 plus lambda minus 2L plus 2. So that's our recurrence relation. Now, if we go back to 3.1, 3.1 implies that R0 is 1. Sorry, 0. So that's the state we can't raise. If we raise the highest weight state, then we get 0. And so we've got a recurrence relation with a fixed point in it, and you can just solve it by induction. Which is like a 3-line exercise left for you. RL is lambda plus 1 minus L times L. Okay, so also because we've picked a finite dimensional irrep, that implies there must be a least weight, because again you could carry on subtracting subtracting from the eigenvalue with the ladder operators to have an infinite dimensional representation. So it must be of the form of the highest weight. Well, since we get 2 from subtracting, from acting with E minus, you're going to get some multiple of 2 subtracted off it. So if we take a vector which isn't 0, so this is going to be the state with least weight. Then if we try and lower it again, then we do get 0. Okay, this is defined to be, by the above equations, this is defined to be V lambda minus 2n minus 2. And that implies that Rn plus 1 is lambda minus n times n plus 1 is equal to 0. Okay, so really this equation tells you that Rn plus 1 is 0, and if I just plug in L equals n plus 1, this is the expression that I get. When is this going to be equal? Well, it's going to be equal to 0. It's going to be 0 when lambda is equal to n. So I can summarize all of this. So these are the finite dimensional representation irreps. Finite dimensional irreps of the Lie algebra of SE2. These are d lambda, where lambda is in natural numbers including 0 with the following properties. D lambda has weights. Well, it's got the highest weight lambda, and you can subtract off 2 off this up to n times. So that set is in the integers. Each weight has multiplicity 1. And the dimension of our representation is lambda plus 1 for lambda bigger than 0. But the dimension of 0 of lambda equal to 0 is 0 for the Lie algebra. Okay, that's it. So as I say, that is going to be useful for analyzing representations of more general Lie algebras.